Hello everyone, welcome to this lecture in the Neural Network from Scratch series. In the last lecture, or up till now rather, we have looked at how to code an entire forward pass in Python. So we have reached this stage in our Jupyter notebook where we have coded an entire forward pass by chaining together layers and activation functions. So if you have not watched the previous videos, either you can watch them or you can take the Jupyter notebook which I am providing in the video description and you can run the previous code blocks. Up till now, we have not looked at the loss function. However, loss function is one of the key areas which makes neural network really powerful. Without a loss function, there is no way to optimize a neural network because we would not know whether we are doing a good job or whether we are doing a bad job at our uh, task in hand. So, what is the task which we are looking for? The task is that we have this data set which is called as spiral data set, and every input has two attributes x1 and x2, and these inputs belong to either of three classes: red, green, or blue. Our task is whenever a new input is given, we should be able to predict which class it belongs to correctly. Okay. The reason we start looking at loss functions is because when a neural network is initialized, such as what we saw in the forward pass, the weights are initialized randomly, and so the output for any given input which you have may not be correct. It may not be corresponding to the actual class. So for example, if you look at this neural network with two hidden layers, three neurons each, and let's say I give an x1 x2 which is maybe this point here, which is the red point, and I feed it into the neural network, and the outputs in the final layer are some outputs. If the weights of the neural network are not optimized, we may get a wrong answer most of the times. But to start optimizing the weights, we need an indicator of how well we are doing. So if we are doing bad, then we will update the weights so that we start having a good performance. That's why we need to define the loss function. There are a number of loss functions such as the squared loss, the cross entropy loss, etc. But since we are looking at a classification task here, I'll be looking at or rather explaining a loss which is called as categorical. It's called as categorical cross entropy loss. So the idea behind this loss is very simple. We have a softmax activation function at the last layer output, right? So the three neurons in the last layer will give some outputs between the range of 0 to 1. So the output of the first neuron is the confidence that the current input belongs to the R category or the red. The output of the second neuron is the confidence that the current input belongs to the green category, and the output of the third neuron is the confidence that the current input belongs to the blue category. All these confidences add up to 1 because they represent probabilities. The ideal answer which we want, especially for this input which belongs to the red class, is 1, 0, and 0, because it does not belong in the green class and it does not belong in the blue class. So if we get an output from this particular output layer as zero point 0.5, zero point 0.5, and 0, it means that we are 50% probable that this input belongs to class red, and we are 50% probable that it belongs to green. So our weights are not optimized at all. But if we get an output as this, then it means that with 100% confidence we can think of the input belonging to class red. So intuitively we know that if we were to think of a loss function, the loss for this will be much higher than, let's say, the loss for this. In fact, we can even take an intermediate thing as zero point 0.8, zero point 0.2, and 1. If you compare this output versus this output, where do you think the loss should be higher? Of course, in the first case, the loss should be way higher because here we are 80% sure that it belongs to the class red, whereas here we are 50% sure that it belongs to the class red. So this is better than this one here. So we have an intuitive understanding of uh, If we see the output, we'll know which loss is higher and which loss is lower. But now we need to define a mathematical function for it, and this mathematical function is called as the categorical cross entropy loss, especially for classification tasks such as the one which we are considering. And the formula for this is negative of the true label multiplied by the logarithm of the predicted label. So consider this case in which, let's say, our predictions are zero point 0.7, zero point 0.1, and zero point 0.2, and the true label is 1, 0, and 0, because the input belongs to the red class. This is the true label, and this way of representing the true label is also called as one hot encoding. So if the input belongs to the red class, it will be represented as 100. So RGB. If it belongs to the green class, it will be represented as 010, and if it belongs to the blue class, it will be represented as 001. This is one hot encoding. So let's say these are our predicted values, zero point 0.7, zero point 0.1, and zero point 0.2 from these three output neurons, and the true value is 1, 0, and 0. The categorical loss cross entropy loss formula is you take a summation. First, you add a negative sign and you take a summation between the true value and you multiply it by the log of the predicted value. So, let us scan this neuron by neuron. So, the true value is that only the first neuron needs to be activated. So, for the first neuron, the true value is 1. So, the first term will be 1 into log of zero point 0.7 because the predicted is zero point 0.7. The second neuron, it ideally needs to be deactivated because there is no green prediction in the current input. So for the second neuron, it is 0 into log of zero point 0.1, and for the third neuron, it is 0 into log of zero point 0.2. So then the answer will be negative of log of zero point 0.7, which is 0.3566. Let us take another example where we have the outputs as zero point 0.5, zero point 0.1, and zero point 0.2. The loss in this case would be negative of true value for the first neuron is 1 because the correct answer is red. 1 into log of zero point 0.5 plus 0 into log of zero point 0.1 plus 0 into log of zero point 0.2. Okay. So this answer would be 0.69, whereas if you do this calculation for this predicted value, zero point 0.7, zero point 0.1, and 2, it will be 0.3566. So you will clearly see that if we have 50% confidence in the first prediction, we'll get a higher loss compared to, let's say, if we have a 70% confidence in the first prediction, we'll get a lower loss. The first thing which I want to note here is that the incorrect classes don't matter at all because their coefficient is 0 anyways. So the simplest way to calculate the cross entropy loss is to just look at, so if you are given a data point, look at its true value. So in this case it's R, and then just look at the predicted, just look at that, the confidence of that particular class. So here it's 70%, so the loss is negative log of zero point 0.7. If it's zero point 0.5, the loss will be negative log of zero point 0.5. So the simplest way to do this is that, let's say we have an input x1, x2, the first layer and the second layer. If the input is 100, which means red, we only need to look at the output of this neuron. If the output of this neuron is zero point 0.5, the answer is negative log of zero point 0.5. This is the loss. If the answer is zero point 0.7, the answer is negative, the loss is negative log of zero point 0.7. And if the answer is zero point 0.9, the answer is negative log of zero point 0.9, which is the loss. And if it is 1, then the loss is negative log of 1. And this is the loss. So now let us plot actually negative log. So if you take x-axis and if you plot negative log of x, it will actually look something like, so the log looks like this. So the negative log looks something like this. and our x is probability, so it will always lie between 0 and 1 anyways. So the reason we take the negative sign is for the loss to be positive. So we are always going to lie on this side. We are always going to lie on this portion of the loss because our input is always going to be between 0 and 1. Now let us look at the different inputs. So if the input is zero point 0.5, so if the input is zero point 0.5, let me reduce the thickness here further. uh, okay, so if the input is zero point 0.5, it may lie somewhere here, and the loss is somewhere here. And in fact, I think this loss is around zero point 0.7, the actual value if you take the log. 0.7. Now, if the input on the other hand is zero point 0.7, its loss will be lower. It will be around 0.3, 0.35. So as you can see, if we move to the right hand side of this input, the loss actually decreases. And if we move to the answer 1, then the loss actually becomes 0. And that's exactly what we wanted, because if the prediction of this first neuron is 1, it means that we are 100% confident that this input belongs to the red category. So negative log of 1 is anyway 0, so this will be 0 loss. So remember that if we are on the left side here, it means our prediction is low confidence, so the loss will be very high. But if as we keep moving to the right, then our confidence increases, and this actually means that we are entering high confidence that it's the correct answer. So the loss actually starts to decrease like this until it becomes 0 if the input is 1. That's why we take the negative. First of all, we take the negative because we want the loss to be positive. And the reason we take logarithms is because our inputs are probabilities. So if the input is 1, we want the loss to be 0. That's why we take log, because the logarithm of 1 is equal to 0. This is the intuitive meaning behind why cross entropy loss is defined like this. Formally, it's defined as this summation, but for incorrect classes, the coefficients are anyway 0. So all we need to do is that, let's say, if this is my network and if the input is 0 1 0, then we only need to look at the output of the second neuron and take negative loss of that. Whereas if the input is 0 0 1, then we only need to take the output of the third neuron and take the negative loss of that. So this is how we'll define the cross entropy loss intuitively, and this is the mathematical formula for the categorical cross entropy loss. The reason it's called categorical is because in this case we have three categories, right? Red, green, and blue. So this loss is typically used in classification problems. Now let us actually look at how to code this categorical cross entropy loss in Python. Okay. So we are going to take two cases. In case number one, the class targets are just numbers. So maybe red is represented as 0, green is represented as 1, and blue is represented as 2. So for all these inputs in this spiral data here, for all these inputs, there will be an output value. And in this case, we are assuming that those are just numbers. So every input will have numbers corresponding to 0, 1, and 2. So let's say that let me draw a simple neural network here. So let's say that we have an input coming in, and then these are the layers, and this is the layer, and then these are the outputs. So every batch of data will have three outputs. So here I am showing three outputs from three batches. So if you look at the first row, this is the output from the first batch of data from three neurons. Here we can see that with 70% confidence we think it's a red. Uh, for the second batch, we think with 10% confident it's red, 50% confident it's green, and 40% it's blue. For the third batch, we think that with 2% it's red, with 90% it's green, and with 8% it's blue. Okay, and the true labels for these classes are, so let me remove this uh, this thing here. The true labels for these classes are red, green, and green. These are the true labels. And this will be represented as 0, 1, and 1, because that's how the labels are represented in this case. Since we don't have blue, the output labels for the first batch is 0, the output label for the second batch is green, the output label for the third batch is green, which is 1. Your task now is that given these outputs from our neural network and given the actual data, try to find the loss function. Now, as a mathematical exercise, this should be pretty simple because of the trick which I have taught you. Let's look at it batch by batch. So, in the first batch, remember what I told you, always look at the correct answer and then only look at the confidence of that particular class. So, in the first batch, the correct answer is red. So, I only need to look at zero point 0.7. So, the loss from the first batch loss will be just the true label, negative of the true label into log of the predicted label, right? So the first batch loss will be negative of 1 into log of zero point 0.7. The second batch loss, for the second batch, the true label is green. So we only need to look at the output of the second neuron. So for the second batch loss, it will be negative of 1 into log of zero point 0.5. And for the third batch, we also, the output is green, so we need to look at the second neuron. So for the third batch loss, it will be negative of minus 1 into log of zero point 0.9. So ideally, if I were to have a loss vector, it will be minus log of zero point 0.7, minus log of zero point 0.5, and minus log of zero point 0.9. This will be my losses, and then I'll just add these losses and maybe take an average to find the representation of the loss. So this has been represented formally here. So the first data loss, if you use the actual entire formula of the cross entropy, it will be minus 1 into log of zero point 0.7 plus 0 into log of zero point 0.1 plus 0 into log of zero point 0.2. So only thing which will survive is the first element, which was what we had written over here. If you look at the second data loss, it will be negative of 0 into log of zero point 0.1 plus 1 into log of zero point 0.5 plus 0 into log of zero point 0.4. So the only thing which will survive is this, as has been written over here. And for the third data, the loss is negative of 0 into log of 0.02 plus 1 into log of zero point 0.9 plus 0 into log of 0.08. So the only thing which will survive is this second quantity. Okay, so these are the three data losses. So if you look at this array, we actually only need the first index from the first row, the second index from the second row, and the second index from the third row. All these other indices don't matter at all. And how do we do that in Python? So we just need the 0th index of the first data, because Python has an index system which starts from 0. So we need the 0th index of the first data, first index of the second data, which is this, and the first index of the third data. And we just need to take negative log of those. So we use an advanced indexing operation in Python. So let's say this array is called softmax outputs. So look at this particular operation, softmax outputs, and then the first argument is 0, 1, and 2. And the second argument is class targets. So the class targets, as we have seen, are just 0, 1, and 1. So the class targets will be 0, 1, and 1. The way Python executes this code is that it means that for row 0, select element at column 0. For row 1, select element at column 1. And for row 2, select element at column 1. Let us see how this works. For row 0, we will select element at column 0, which will be exactly zero point 0.7. For row 1, we will select element at column 1. For row 1, select element at column 1. So this is row 1 and this is column 1. So we'll select zero point 0.5. And for row 2, select element at this. So this should be column 1. For row 2, select element at column 1 because the third value here is 1 and the third value here is 2. So for row 2 also we have to select column 1. So it will lead to this value of zero point 0.9. So what this operation will do is that if we index the softmax outputs like this, the only values which we'll get is zero point 0.7, zero point 0.5 and zero point 0.9, which are exactly the values which we needed. And then all we need to do is we need to take a negative log of this and we need to take the mean to find the cumulative loss of this data set compared to the actual data. Let us see now how this is executed in Python. So we are at the cross entropy loss building blocks in Python. So let's say these are the softmax outputs array, which we have seen over here. This is the softmax output array. This is the class targets, red, green and green, 0, 1, 1. So now first thing what I want to show you is this command softmax outputs and then 0, 1, 2 and class targets. So what this will do is that it will look at let me write it here again. What this will do is that there are two attributes, right? 0, 1, 2 is the first, and the second is class targets, which is 0, 1, 1. So what Python will do is that it will look at 0, 1, 2, it will look at 0, 1, 1, and then it will look at the this. So zeroth row and zeroth column. So it will retain the zeroth row and the zeroth column. Then it will look at these two. Then it will retain the first row and the first column element, and then this. And then this will give the second row and the first column element. So then only those elements which will survive, which have the correct class. That's why the second argument is class targets. So only these elements will survive, zero point 0.7, zero point 0.5 and zero point 0.9. And then we just take the negative log of this and then take the mean. So without taking the mean, if you just use the negative log, you will get this. You will get a loss value for each particular data. So for the first data, look at the loss value is 0.35. For the second, it's 0.69. And for the third, it's zero point 0.1. Can you guess why the loss is so low for the third data? So look at the third data with 90% confidence. It says that the value is green, which is a correct value. So it has a more confidence. Whereas in the second data, with only 50% confidence, it says it's green. So the second data loss is much higher than the third data loss. And then you have to just take the mean of these three entries to give you the cumulative loss. Uh, so you just take the mean of these and get the cumulative loss as 0.385. Okay, so this is how you calculate the cross entropy loss in Python. But this was a case in which the class targets were just numbers 0, 1 and 2. In most classification problems which you encounter, the class targets will be encoded with something called as a one hot representation. So we looked at three data points here, right? Or three inputs whose true values were 0, 1 and 1. Instead of just writing them as 0, 1 and 1, in one hot vector representation, we start with, let's say if we have five categories, we start with 0, 0, 0, 0, 0. And if the answer belongs to the first category, we just replace this by 1. If the answer belongs to second category, we replace the second category by 1. If it belongs to the third category, we replace the third category. This method of encoding class labels, it's called one hot encoding, and it's very commonly used in classification problems. So this is how the one hot encoded inputs will look like. So for the first input, the true value is red. So its label will be 100. For the second input, the true value is green. So its label will be 010. For the third input, its true value is again green. So its label will be 0, 1 and 0. Now the question is that if we have this particular array, how will we only take indices which matter to us? So how will we uh, only keep zero point 0.7, zero point 0.5, and zero point 0.9. In the previous example, when the class targets were just numbers, we could just index with class targets, right? But now the class targets are not numbers. So what should we do? So let's write down these two arrays side by side. So this is my class targets array, which has been written on the left hand side over here. And this is my prediction array, which has been written on the right hand side. Okay. What I want you to do now is to do an element wise multiplication. If you do an element wise multiplication of these two, you will realize that from the first row, what survives is only zero point 0.7. From the second row, what survives is only zero point 0.5. And from the third row, what survives is only zero point 0.9. This is exactly what we needed, right? We needed zero point 0.7, zero point 0.5, and zero point 0.9 to survive. All other entries do not matter. So then all we need to do is do an element wise multiplication of the class targets with the prediction, and then we just have to sum the columns. So we sum, so this is the first column, second column, and third column. So we just sum the first column, second column, and third column. So that's it. We directly get zero point 0.7, zero point 0.5, and zero point 0.9, which we obtained through this earlier method also. And then we just take a negative log of this and then take the mean, similar to what we did for the earlier case. So remember that if the class targets are not just numbers, so when class targets were just numbers, it was just one dimensional. But if the class targets are one hot encoded, then they are two dimensional. And the way to get the loss is that you just take the element wise multiplication between the class targets and the prediction, and then you just sum it column wise. Then you take a negative log and then you take the mean. That's it. It's as simple as that. So let us see how this is implemented in Python. So let's say if you have a one hot array which looks like this. So actually let me use exactly the same example what we used here. So if the first element is 1 0 0, the second will be 0 1 and 1, which is green, and the third will be 0 1 and 0, which is again green. So let's say this is the y true, and let's say these are the predicted values: point 7, point 1, point 2, point 1, point 5, point 4, and 0 0.2, 0 0.9, 0.08. Here I have just replaced it with different values, but it holds very similarly for this case as well. Or actually, let me just use the same ones. So this point 0.7, point 2, point 1, this is point 1, point 0.5, and point 0.4. And the third one is 0.02, 0.02, point 0.9, and 0.08. Now, first thing which I am going to show you is do an element wise multiplication. Remember, if we use np dot dot, then it does a matrix multiplication, Python. But if you just use a multiplication sign, Python will do an element wise multiplication. So if you run this, you will get zero point 0.7 in the first row, all other entries will be 0, zero point 0.5 in the second row, all other entries will be 0, and zero point 0.9 in the third row, all other entries will be 0. Exactly like what we had written over here. Okay. And after this, what you need to do is that, let me just call this as a, this array. Then you just need to do np dot sum a comma axis equal to 1. Let me see if this is actually correct. Np dot sum a comma axis equal to 1, and let me run this now. Great. So then we again get zero point 0.7, zero point 0.5, and zero point 0.9. And then we have to do the same thing. We have to take a negative log of this matrix, this array, and take the mean of this. So then, so let me say B is this summation, and then C is equal to negative of np dot log B. So let me run this, and let me print C. So then C will be these loss values, which is exactly same as the loss values which we have gotten if the class labels were just numbers. And then I will just take np of mean C, and let me print this. So then we get a cumulative loss of 0.385, which is exactly the same loss as we had gotten earlier. So depending on the how the class targets are, the procedure should vary differently. So if the class target is just written as numbers, you can do this clever indexing in Python and then take the negative log. But if the class targets are one hot encoding, then you first need to multiply the class targets with the prediction, take the summation along the columns, and then take the negative log. So one thing which I wanted to show you is that earlier I had written this as 0, 1 and 2, right? So I had written it as 0, 1 and 2. This can also be written as range of 3, and it leads to the same answer. So, and what is 3? It is the length of this output. So every data has 3 elements, right? So this can just be written like this. So depending on the shape of the labels, you can either use this, the clever indexing, or you can use the element wise multiplication, then axis summation, and then taking the log. Okay, now one more thing which we are going to do is that this is the prediction matrix, right? And eventually we will take a log of this prediction matrix. So we need to make sure that we do not have very large or very small values when we take this log. So we will just clip this prediction matrix. So what this clip function does is that uh, you give a minimum value and you give a maximum value. So by giving it a minimum value, it prevents any value here from becoming zero. Because if it becomes zero and you take a log of it, it leads to a big problem. Uh, and we also prevent it from becoming exactly one. Because if it is one, the loss would be zero, and that won't be too good for taking gradients. So we will keep it just very close to one. So the input values will not ever be zero and will never be one, so that we avoid the issues when we take logarithms. And we also don't want any element to be zero, because that would lead to some issues when we take the gradients. So when I'm going to show you the loss class right now, you will see this clip function, but it has a very simple function which I just demonstrated to you right now. So now let us look at the loss, the categorical cross entropy loss class, and how to implement that in Python. Okay. So here's the loss categorical cross entropy class. It has one method which is called as forward. What this method does is that it takes two inputs. It takes the prediction, which is this array here. This is my prediction array. So the forward method of the loss categorical cross entropy class takes in this as one input, and the second input it takes is the class targets, which is y true. Okay. uh, as I told you, here is the clipped version of the y prediction to avoid the predicted values from being 0 or 1. What it does later is that it checks whether the shape of the true value is one dimensional or two dimensional. So if it's one dimensional, it means that it's the case one which we had seen. So class targets are just numbers. Whereas if it's two dimensional, it means that the class targets are one hot encoded, right? So if it's one dimensional and the class targets are just numbers, we use this clever indexing, where we take the predicted and we use the range of samples as the first argument. So remember, this is exactly what I mentioned here. And the second argument will be, or the second value would be the true. So then it will only keep those values in the prediction which are actually needed. Whereas if the true values are one hot encoded, then we will take the element wise multiplication and sum it along the axis. And so it will lead to an output which looks something like without taking the log. So then we will only have zero point 0.7, zero point 0.5, and zero point 0.9. What we will do is that whether the shape is 1 or whether the shape is 2 of the true labels, whatever is the result, then we take the negative of the log. and then we return what is called as negative log likelihood. So when you take the negative log of every element, this matrix which you get is also called as the negative log likelihood. And what this array will be it will be something like this. Up till now we have not taken the mean, but we are just printing out the loss for every batch, or this. So this is the output of the categorical cross entropy loss. Now there is one more class which has been defined, which is called as the loss class. And what this class will do is that this class will take the mean of whatever output was given in the loss categorical cross entropy class. So basically, ultimately, what we will be doing is that we will be defining an instance of the loss categorical cross entropy, and then we will be uh, calling the loss class so that it will take the mean and return the final loss. So if you look at the loss class, since it is an attribute or an argument of the loss categorical cross entropy, the loss class will inherit the methods in this class. So it will inherit the forward method. So when you call the loss class, it will first calculate the array of losses or the negative log likelihood, which is this array, and then it will take a mean, and then it will return the final mean as the loss. Okay. The reason we implement one more class like this is just for the sake of simplicity. Instead of making this loss categorical cross entropy also return the mean, we only return the negative log likelihoods here so that we can also see the weight values. So here is a simple demonstration of how these classes work. Let's say these are the softmax outputs, which we had already seen over here. And let's say these are our class targets. So this is the one hot encoding. These are the class targets and these are the softmax outputs. We will first call the loss categorical cross entropy, and then we will use the calculate method here. So once we use the calculate method, we will get the output of the loss function, which is the negative log likelihood array, and then we will find the mean. So then the mean is printed out as 0.385, which is exactly the same mean as we had obtained earlier. So this is the advantage of writing classes in Python. It's within 6 lines of code we got this answer right now. So now I want to briefly show what all we have covered up till this point. We have indeed covered a lot of things now. Um, so let me actually show you what all we have covered. Okay, so we have coded a neuron, we have coded a layer, we have coded many layers, we have coded activation functions. Now we have also coded a loss function. And now we are ready to make a forward pass with this loss function. So in the last lecture, I already showed you how to make a forward pass without the loss function. So you chain the layer dense class with the ReLU class with again a layer dense class with the softmax class. Now we will add the loss function also here. So this is how this is done in code. We first create the first layer class, then we create an instance of the ReLU activation, then we create an instance of the second layer, then the softmax activation, then we create an instance of the categorical loss cross entropy loss. From this point we begin the forward pass. So dense one dot forward, this is the layer 1 output. It is then passed into the activation of the first layer, which is the ReLU. Then that is passed into the second layer, which is passed into the activation of the second layer, which is the softmax. And then we print the softmax outputs, which are these. Then what we do is that we then calculate the loss function between these outputs. Remember, the loss function takes two arguments. First is the predicted value and the true value. So the true values are actually written over here when we created the spiral data set. So then we have the loss function and then we print the loss. So here you can see that the loss is 1.09866193 for this particular output. You can see that the output is not very good because it assigns a 30% probability to all the classes, red, green and blue. So it's one of the worst losses. Uh, the ideal output would be where a very high probability is assigned to one class, but here equal probability is assigned to all classes, and this is reasonable because we have not optimized the weights currently. The weights are initialized randomly. Now I am going to introduce another metric which is used to measure the performance of our neural network, and that is called as accuracy. uh, Accuracy is a much more simpler feature or much more simpler metric than categorical cross entropy loss, and it's very easy to calculate. What accuracy says is that um, if this is the let's say, let me show you the output. Yeah, if this is the output of our neural network, accuracy just says that you look at each row and try to predict which class is that row trying to predict, irrespective of its value. So here, although this first value is not 1, it's still the highest among these three values, right? So if you just look at the first row, it is trying to predict class 1. If you look at the second row, it is trying to predict class 2. And if you look at the third row, it is also trying to predict the class 2. So first row is trying to predict red, second row is trying to predict green, and third row is trying to predict green. So then the accuracy is 100% here. In accuracy, it does not matter uh, whether 70% is not 90% or not 95%. As long as with the highest confidence we are predicting class 1 among these three classes, we call it accurate. So that's what's done. We take the maximum argument in each row and we check it with the class targets. And the number of times we are correct, our accuracy increases. So in this particular case, if you look at the first row, the maximum index is 0. If you look at the second row, the maximum index is 1. And if you look at the third row, the maximum index is 1. So it's 0, 1, 1, which is exactly similar to the class targets. And so the accuracy will be 1 in this case. So as you can see, it's not really a great metric because it does not tell us how close or how far we are. But when training large neural networks, we often plot accuracy over a function over a period of time as the weights continue to optimize themselves and weights continue to change. So these are the two metrics which we have introduced in today's lecture. We have introduced the categorical cross entropy loss, and we have introduced accuracy as a metric. And I've showed you everything through code as well as through a theoretical foundation in a whiteboard format like this. So thank you so much everyone, and thanks a lot for sticking with me up till this point. There are a lot of fun things to follow such as calculus, gradient descent, optimization, etc. So looking forward to seeing you in the next lectures.